hello. In theory, yesterday we did some problems on measuring the center of a set of data, mean, median, mode, and the spread of a set of data, mainly range and standard deviation. Did you really do it? I guess we'll never know. However, I'm going to go over the answers for you right now. Let's start with, I don't know, number one. They give you a frequency table with a number of scores. They ask you for the class mean to the nearest integer. Very common mistake I see on this is students will just add these up and divide by 6. Well, that's not really how many tests there were, because there were 5 of these, 7 of these, 9 of these, etc. So you do need to be careful with the frequencies. What we really want to do is something more like this: 575s, 780s, 985s, etc., etc. In all, there were 36 total scores, and when we divide 3100 by 36, we get 86.1 repeating. It did say to round to the nearest integer, so we'll take 86.111 to 86. Number two, basically doing a very similar thing, this time with a bar graph, and this time instead of the mean, we're looking for the median. If you add 4, 8, 6, 10, and 3, you get 31. We like that because that means there's going to be exactly one number in the middle. We take 15 off each end, and there you go. You get an 80. Now, I guess you could have done this right from the graph if you played a little game called 4 off this side, 4 off this side, 8 off this side, 8 more off this side. There's one more up here, isn't there? So let's take that one and that one. Looks like the only numbers left are 80s. So the middle 5 numbers are all 80s. That means the median would have to be an 80. Number 3, for this set of 5 numbers, which of the following must be true? You could actually answer this very quickly just by putting them in order and realizing that the mode was an 8 and the median was an 8. If those two are equal, the only one of these answers, it tells us that the mode and the median are equal with C. Boom, you're done. However, for those of you who like to be a little more thorough, we could have calculated the mean and the median and the mode, and sure enough, they are all 8. Number 4 and 5 went with this particular histogram, right? Another name for a bar graph. The first one was just asking what the range was. Well, the lowest data point is 0. The highest data point is 4. And we know that 4 minus 0 is 4. The range is 4. That was exciting. Number 5, what is the median number of volunteer hours completed? So once again, you could do the deal where you take 4 zeros and 3 ones and 5 twos and put them all in order. And this time there's 2 middle numbers. There's, I believe, 14 total data points. So the middle numbers would be the 7th and 8th, and the average of 1 and 2 is 1.5. You could have gotten to the same point if you did, okay, 4 off that end, 4 off that end, 3 off this end, 3 off this end. Oh, look, I have 1, 3, or I'm sorry, 1, 1, and 1, 2 left. So average them, same answer, different way of doing it. Number 6, what is the range of these heights from 100 high school orchestra students? Well, it's going to be probably a little trickier to come up with that if we stay in feet. But if I convert them into inches, it becomes very simple to do 67 inches minus 58 inches to get 9 inches. Now, the seventh question is the first one that references standard deviation, which was a big part of yesterday's lesson. And some of you may remember, oh yeah, Mr. Yansak told us about normal distribution and the 68, 95, 99 rule, and you could have gone right to work. But I imagine a lot of you guys got to this point and were thinking, standard what? So here's a quick recap on standard deviation, okay? The best definition for you probably is this one, which tells you that the standard deviation is the average amount, okay, by which the data points differ from the mean. So basically, the average distance of all the data points from the mean. That's what we're looking for. This was the example I gave you, 5 data points, which had a mean of 7.6. How far is each one of those individual data points from 7.6? Remember, we looked at those numbers, we added them up. Now, that didn't exactly equal the standard deviation because it's a slightly more complex equation where we're adding up their squares. So it's really like 3.6 squared plus 2.6 squared plus 1.4 squared plus 0.4 squared plus 4.4 squared. And then after we add them up, we take the standard of the square root. So it gives us a slightly different number, but that in essence is what we're doing, is we're averaging the distance. That's what the standard deviation is. And furthermore, there was this really important, what's the word we're looking for here? Percentage breakdown of a normal distribution, where within one standard deviation, we can always find 68% of the data, 34 on each side of the mean, and then 2 standard deviations out gives us 95%, and so on. The empirical rule is officially what you'll generally hear this called, empirical rule for a normal distribution, but most students just remember it by the 68, 95, 99 rule. And so with that in mind, here's how we're going to do this problem. They want to know the best description of heights falling within approximately 1 standard deviation from the mean. So we know that within 1 standard deviation is roughly 68% of the data. So it's easy to take 68%, right, of 100, it's 68. And if there's 68 and then we subtract that from 100, since there were 100 students, that means 32 students are not within 1 standard deviation. And because of the symmetry to the normal distribution, that means that 32 breaks down into 16 on each side. So there's going to basically be 16 students in this area, 16 students in this area. And we're going to kind of use that idea here to solve this problem. We're going to take 16 low squares. So there's 8 right off the top there. And here's another 8. So now we have 8 more to go on the bottom and the top, right? Well, this 10 is going to be too many. So what I'm going to do with it basically is I'm going to split it, right? I'm going to split it into a 2 and an 8. And then I need to get rid of 8 of those. So that's 8 plus 4 plus 4 is 16. I can get rid of this entire 6 here. Now that's 14, but I only need 2 of the 16. So I'm going to get rid of 2 of those 16 right there. And there you go. That's 68% of the data points that are left. Now, the top point's pretty easy to see. 64 inches is 5'4". 60 inches would be 5 feet exactly, but because there were only 2 of the 10, I believe they just bumped that up to the next big group of 61 inches, which was 5'1", which is why the answer is C. So you really had to use that empirical rule to do this particular problem. Number 8 is one of the first of many problems where we're just going to set up an equation, solve for a variable. We have Anton, who has 4 grades, and we know that his total average was 85. We want to know what his missing score was, okay? Well, I guess let's see here. He wants to get an 85 average. I guess that's what it is. So we're going to add these 4 scores together with an unknown 5th score, and then divide by 5 since there's 5 tests. So we're going to set that equal to 85. That's just basically an equation for averaging 5 numbers. I'm going to multiply by 5 here to get the 425 and get rid of the 5 in the denominator. The 4 scores we already have add up to 333, and when you subtract, you get 92. Boom. This bottom question, very similar. The mean grade on a test taken by 15 students was 70. When one more student took the test, the entire average raised to 71. What score did that student take? You could do a little logic here, and you could say, look, we're gonna raise the entire average by 1 point. That means the original 15 students, this student that's taken it, has to score 1 point for each of them. So that's 15 points right off the bat. But then they need to score an extra point for themselves. So that's a total of 16 points higher than a 70, and 70 plus 16 is 86. But it's just as easy to set up the algebra, right? 15 70s plus the 1 missing score divided by now not 15 anymore, but 16 students raise the average to 71. Multiply by 16, right? Multiply both sides by 16 to get this 1136. And multiply the 70 by 15 for the old average. And then the subtraction will give you the same answer of 86, which we had previously reasoned. Number 10. The mean grade on a quiz by 8 students is 85. When John took the test, he raised the class average to 86. So very similar. We could use the reasoning that says it's going up by 1 point. So he would have to score 1 point for each of the 8 students plus a point for himself. That's 9 points above the old average to move it to a 94. And 85 plus 9 is 94. But here's the exact same algebra we just saw previously. 8 85s plus 1 new test score divided by 9 test takers now, right? Not 8 anymore. And the algebra by multiplying and then subtracting will give us the same 94. Number 11. The grade on Mr. Maroney's algebra tests were, and it looks like there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of them. Okay. Julie took the test later. Geez, Julie. In class, and the median did not change. So because there were originally 13 test takers, I could take 6 off each edge and find the median was 80. Now think about this. If it didn't change, it has to be an 80, because if it's above or below that, I'm going to have to average it, average the 80 with a number above or below it. So the only possible answer there is 80. Number 12, the average of 3 test scores is twice the median. I mean, it sounds like an equation with a lot of variables, okay? 3 test scores, A, B, and C, when averaged, divided by 3, is equal to 2 times the median. Well, if A is the lowest test score and C is the highest test score, B would be the middle. It's called B, the middle test score. So 2 times B would be twice the median. That's kind of a generic formula. But we actually know they're going to give us the median 12. So I can immediately plug a 12 in here and here. And then they, on top of that, tell me the lowest test score, A, is 7. So really, there's only one unknown in this by the time that I plug my numbers in. And then it's just a simple matter of multiplying by 3, subtracting 19, and finding out that the highest score would have been a 53. By the way, if the first 2 test scores were 7 and 12, and this last test score is 53, I've got an outlier alert going on, because that's way, way, way bigger than the previous scores. Number 13, of 5 exam scores, we had 80, 78, and 92 as the first 3. Okay, and the overall average of the 5 scores was 85. So we can set up that equation by doing the 3 test scores plus A plus B as the unknowns, and then dividing by 5 multiply by 5 and subtract the 3 that we knew, which added up to 249, and the two remaining test scores are 176. There's not much we could say about those. Assuming that there's no extra credit, I guess we could say, well, the highest you could get is 100 if the other one was a 76. Otherwise, the two scores would have to be, between a 76 and a 100. So there's a little bit that we could say about those scores, but we really couldn't say much about them individually. However, they didn't really ask us to. They only asked us for the mean of those two scores. So let's divide them by 2, and the mean of those two scores would be 88. Number 14. In a class of 28 students, a certain number of students earned a mean of 76, and another set of students had a mean of 88. What must be true? This is more of a conceptual question, and I didn't draw all 28 scores out here. But if you have a big cluster here of 76s, and you have another big cluster here of 88s, there's no way that the average of a bunch of test scores that average to 76 and a bunch that average to 88 could be above an 88. Those 76s are going to pull it down, or below a 76. Those average 88s are going to pull it up. Now remember, these aren't all 76s and all 88s, but that's certainly what they average to. It's going to have to be somewhere in the middle, and that's answer D. 15 is also a conceptual question. If you have a bunch of scores that average to a 73, and one more score is added in, and it's a 75, it certainly can't lower the average. We don't have enough specific information to know that it's going to give us a mean of 73.5. We'd have to know more information about how many tests there were to know that. But we know for sure that it is going to raise that 73 to some extent. So that one is going to have to be an A for number 15. Number 16 is just an average problem, but this time we're averaging some binomials. So just be careful with your algebra. 2m plus 3 plus 3m minus 1 plus 7m minus 5 divided by 3. Remember, there's 3 values there. And then it's just combining like terms, right? 12m minus 3 over 3. A lot of times there's not much you can do with that, but in this case, 12 and 3 are both divisible by 3. I can factor out this 3 and then cancel it. And so the average of those 3 binomial expressions is 4m minus 1. 17 and 18 are very similar to each other. They give us an average information about 2 numbers and information about 3 numbers, and then asks us something about all 5. And if you just take it in chunks, it's actually pretty simple. If you try to deal with all 5 immediately, there's not much you can do. But here's what we know. We know that the average of P and Q is 20, right? So that means P plus Q has to be equal to 40. We know that the average of R, S, and T is 60, true? So that means that the sum of R, S, and T has to be 180. So when they ask me for the mean of all of them, I know that P plus Q plus R plus S plus T divided by 5 is really just 40 plus 180 divided by 5, which I can actually come up with a very specific mean, 44. Notice that exactly halfway between 20 and 60 is 40, but there were more scores that average 60 than average 20, which is why we're a little bit above that 40. Watch this. This is the same type of math, just different numbers. A and B have to add up to 20. X, Y, and Z have to add up to 60. So that means A plus B plus X plus Y plus Z, right? Has to add up to 80, right? And then 80 divided by 5 is exactly 16. Number 19 gets us back into this discussion on standard deviation. And it gives us the normal distributed data with a mean of 50. So the mean is going to be, bam, 50. But it also tells us the standard deviation is 5, which means if we go out 1 standard deviation, we'll be between 45 and 55. And if we go out 2 standard deviations, we'll be between 40 and 60. So let's just kind of test these out, all right? All the data is between 40 and 60. All the data. That might be a bit of an overstatement. I would say most of the data is, because remember, two standard deviations is 95, but 95 is not all. 95 is not 100%, so that is not going to be correct. 2/3 of the data is less than 55. 2/3 of data is less than 55. Well, remember, 68% of the data, a little more than 2/3, is just between one standard deviation. That would just be between 45 and 55. So when we drop below 45, we're adding to that. So it's going to be significantly above 2/3. So that can't be right either. What about 47.5% of the data is between 40 and 50? Well, let's break that down. Between one standard deviation is 68, which when you divide 68 by 2, you get, what, 34 and 34. Two standard deviations is 95%. So if you divide 95 by 2 to get, 95, half of 95 on each side of the mean, that is 47.5. Boom, there you go. And so that's how we break that down. If you just remember 68, 95, 99, you can do most of these standard deviation problems. I know this is probably a new concept for most of you, but the empirical rule is a big deal moving forward, especially in statistics. Here is another one. A has a standard deviation of 6 and B has a standard deviation of 9. Based on this information, what do we know? Well, not much, because we don't know how many things were in set A and how many were in set B. But because the standard deviation of set A is only 6, that set of data has to be less spread out than set B. Bigger standard deviations mean it's more spread. Smaller standard deviations mean it's more tightly packed toward the mean. So D says that the data in set A is varies less than set B. 21. This is probably the most fun algebra problem on here. The mean of 4 unique positive even integers is 12. So let's just call our integers A, B, C, and D. Okay. Now, unique means different. There can't be any duplications. Positive means above 0, and even means that they have to be 2, 4, 6. They have to be divisible by 2. Now, I could quite easily multiply by 4, right, and get a little bit easier here. But if I want to know what's the greatest possible value for one of these, the best way of attacking that is to know which are the 3 smallest possible values. So the way that D could be the biggest is if A, B, and C were the absolute smallest. You can't use 0 because it's not positive. So the 3 smallest even positive numbers are 2 and 4 and 6. And once you know that, it's pretty simple to subtract 12 and get 36. That's the answer. By the way, 36 is a very special number. Not only is it the 6th perfect square, right? So we've got the perfect square is 1, 2, 2. 2 squared is 4. 3 squared is 9, right? 4 squared is 16. 5 squared is 25. And then, of course, 6 squared would be 36, but it's also a triangular number. Triangular numbers are what you get when you add one more each time, and you get these perfect equilateral triangles. So we don't really get a triangle with 1, but then we add 2, and we get 3, and we add 3 more, and we get 6, and we add 4 more, and we get 10. We add 5 more, and we get 15. Now think about the next ones. We would add 6 more dots to get 21. Then we would add 7 more dots to get 28. And sure enough, the next thing we'd add is 8 to get 36. Indeed, I know this is really exciting for you to know. 36 is the only number that is both a perfect square and a triangular number. You should prove that, and maybe we'll get you some extra credit. 22 is another histogram. It looks like Adrian has been collecting stamps for a while, And from 1989 to 1992, um, they bought, let's see here, 300, 250, 400, and 150 for an average of 275 a year. This question just says, if they also bought stamps in 93 and 94, and the total average remained the same, what would the total number of stamps bought in those 2 years have to be? Well, they'd have to still be buying 275 a year. So that doesn't mean that you have to buy 275 each of those years, but the sum would have to be 550, which is 275 times 2 to maintain that average. So this one, for all the wordage, was actually a pretty straightforward problem. 23, for a set of 3 positive fractions, the mean and median will both equal to 1/2. If the smallest fraction is 5/12, what is the largest? Well, here's what we know. Your smallest fraction is 5/12. The middle number, because they told us the median was 1/2, is 1/2, and the largest number is unknown. So if we average those fractions, which means add them together and divide by 3, you're going to get an answer of 1/2. I could multiply both sides by 3 to help, reduce this a little bit. But this is not as fun as some of the other problems because the fractions, there are a couple of different methods to go with. One method is to just get a common denominator, right? 2 goes into 12, so I could do 6/12 here, 18/12 there, and then 5/12 plus 6/12 is 11/12, and when I subtract it, I get 7/12. Or, this is my star of the day, preferable method. Fractions make things harder. Get rid of them. Why not just multiply through by the greatest common multiple of those, the least common denominator, 12, and you're going to get rid of those fractions within one quick step. 12s cancel, you get 5. 12 and 2 cancel, you get 6. Nothing cancels here. This is probably the most common algebra mistake, is forgetting to multiply by the thing that doesn't have a denominator, right? 12 times x is 12x, and then 12 over 2 is 6 times 3 is 18, and now you just have a real simple algebra problem. Simplify, subtract, divide. Same answer. I think that's the easier way of doing this problem. But however you wish to do it. So if you didn't need all of these answers, and this was a long video to watch, I apologize for that. Never feel guilty about fast forwarding through my videos. Most of the time moving forward, I'll probably just go through and give you the answers and then do the answers and go over the problems that are most requested. But if you do want me to explain any of these in more detail, remember at 2 o'clock tomorrow, I'll send out a link. I might do Jamboard again, or I might actually try that Google Meet this time and see if we can try to use the smartboard. It might be a little neater to write on than the Jamboard. These are weird times, and the only advice I can really give you at this point is do your best. Back normal. I know it's tough, but the normal distribution might help you with that, right? Math jokes. Do they ever stop making you smile? I don't know. Probably not. But have a good morning, and the next video you'll see will be a lecture on some ratio and proportion stuff, mostly review. We will see you then.